and some of the questions that were sent by our students. These questions will be appearing on your screens. And the first question that we had, that is in our exams this week, we had define density and state its SI unit. Define density and state its SI unit. So density, definition of density originates from the topic known as measurement 1. Measurement 1 is a topic in Form 1 that talks about the basic physical quantities. These quantities, the basic physical quantities and derived quantities are well explained in that topic known as measurement 1. So density usually has a relationship with two other quantities. One of the quantities that has a close relationship with density is mass, and another quantity is volume. So for us to have density, then we must have the mass and volume. Taking the value of mass, dividing it by the value of volume, at this point we are able to get density. And therefore, from the formula that we are dividing mass and volume, density can simply be defined as the mass per unit volume of a substance. Density is the mass per unit volume of a substance. The SI unit of density is kilogram per cubic meters. The SI unit for density is kilogram per cubic meter. I'll simply give one expression here that will show you an easy way of getting the SI unit of density. That here I have written, we have density is given by, take the value of mass, divide it by volume. So from this formula we get our definition that density is the mass per unit volume of a substance. Therefore, density can be denoted by this sign known as rho. Rho can be calculated by mass, I write M, over volume, which is V. At this point, we can be able to derive the SI unit of density at this point, in which we are having our rho here is equal to, take the value of mass here, the SI unit of mass is kilogram, which is kg, per the SI unit of volume is meters cubed. So at this point, my calculation at this point gives you what we call the SI unit of density. That the SI unit of density is given in kgs per meters cubed. So density can be found using this formula, mass over volume, and through density, which is written using this sign known as rho, we can take the SI unit of mass, which is kg, divide it by the SI unit of volume, which is cubic meters. This one gives us the SI unit of density. So that is one of the simplest means of identifying the SI unit of density and also defining density. Most of the terms in physics are defined using their formulas. Density can also be measured, and along the way we also have another question that explains how the density will be measured. I hope I'll be able to explain that now using what we call the density bottle. Let us look at the next question that appears on your screen, and the question reads, state three precautions. State three precautions when using a density bottle. State three precautions when using a density bottle. What are some of the precautions that you should consider when using a density bottle? So at this point, I draw this diagram in that manner so that this diagram illustrates how the density bottle looks like. The density bottle appears in that manner, so that it has a long neck. It also has a round bottom in that manner. So this is one of the bottles that is used to measure density. This bottle is usually made using a piece of thin glass. So what are some of the precautions that you should take when using this density bottle in order to measure the density? One of the precautions, you can take the note that when handling this bottle, it should be held at the neck. When handling a density bottle, then you should hold it at the neck. The reason as to why we are holding it at the neck is because if you happen to place your hands anywhere on this bottle, then the heat from your body will transfer to the bottle through what we call the thermal equilibrium. And through that process, we are going to have this bottle expanding. You remember that when you subject solids to heat, they expand. When you subject them to cold heat, they will contract. Therefore, when the heat from your body transfers to the density bottle, it will cause some expansion, meaning that you're going to obtain an inaccurate value. The expansion will increase the volume, and therefore, if you increase the volume, you are affecting the value of density. Therefore, when handling a density bottle, it should be held at the neck, or it should be held by the neck, in order to avoid expansion when it is held at any other point. We also have precaution number 2 when using the density bottle, and it says it should be wiped carefully on the outside. It should be wiped carefully on the outside. Why are you wiping it carefully on the outside? When you use a lot of energy to wipe this bottle, and it is made using a piece of thin glass, you might break it, and it might also cause some damage to your hands because it is made up of thin glass, which might damage your hands if you happen to use a lot of energy and break it. Therefore, it should be wiped carefully on the outside. Make sure you don't use a lot of energy to avoid breaking it. The last precaution, that is number 3, when using what we call a density bottle to measure density, you should ensure that there is no air bubble when filling the bottle with a liquid. Ensure that there is no air bubble when filling the bottle with a liquid. At this point, you want to determine the density of a liquid. For example, you want to determine the density of water, or it might be kerosene, or it might be mercury. Therefore, if at all we have the air bubble appearing inside this density bottle, then it means that the density you're going to find at this point belongs to that liquid and the air, which is going to give you inaccurate values. Therefore, you must ensure that when filling this density bottle with a liquid, ensure that there is no air bubble. So those are some of the 3 precautions that you have to consider when using a density bottle to measure density. This density bottle is one of the instruments that you can use. You can use it to measure density directly. By using it, you can use mass over volume and calculate the volume of that liquid. So that was the second question that was asked. I had to bring them together because the 2 questions are related and they actually originate from the same topic. Another question that we had, the question reads, that is, explain why liquids expand more than solids under the same temperature. Explain why liquids expand more than solids under the same temperature. This question originates from the topic known as the particulate nature of matter. The particulate nature of matter is a topic that looks at the different properties of matter and how they behave when subjected to different forms of heat. So at this point, we want to look at why liquids expand more than solids when subjected to the same temperature. So at this time, I'll draw the properties of matter and distinguish them in terms of particle arrangement. That now, at this point, in the particulate nature of matter, we usually have the solids, we have the liquids, and we have the gases. So looking at the solids, if this is one block of a solid, then the particle arrangements in a solid, these particles are usually too close. They are very close to each other at this point, so that they don't have what we call the intermolecular distance. The intermolecular distance between the particle arrangements in a solid is very small. When you go and look at the particle arrangement in a liquid, you'll find that at this point, the intermolecular distance is larger as compared to that of the solids. In liquids, the intermolecular distance is larger as compared to that of the solids. You should not be worried when I speak about the intermolecular distance. The intermolecular distance is simply the distance between one liquid molecule and another liquid molecule. So the distance between the two molecules is what we call the intermolecular distance. And here we are comparing the intermolecular distance in solids and liquids. You can see from your on whatever I've drawn that the intermolecular distance in solids is smaller as compared to that in liquids. What about in gases? In gases at this point, now the intermolecular distance appears to be very large in that manner. So that if you compare the intermolecular distance between the liquids and the gases, you'll identify that the intermolecular distance between two gas particles is very large. So this is how you can be able to distinguish the three properties of matter in terms of molecule arrangement. So at this point, we can be able to explain why gases expand more when subjected to heat as compared to solids. Now let us look. If I introduce or if I subject heat to this solid, what will happen? These molecules will tend to expand. But when one molecule tends to expand, it is still compressed by other molecules, meaning that these molecules are just going to vibrate within fixed positions. They will tend to push one another, but within a very small distance. But look at gases. We have a very large intermolecular distance. Therefore, when I subject this particle at this point, these gas molecules to heat, they are going to expand because they have enough space. Therefore, this can be explained that between two gas particles, we also have the intermolecular forces. The intermolecular forces are the forces that hold two molecules together. So here in a solid, they are close together because they have what we call a strong intermolecular force. So the solid particles have the strongest intermolecular force as compared to liquids and gases. Therefore, these gases have what we call a weak intermolecular force. This weak intermolecular force can simply be broken when these gas particles are subjected to heat. And therefore, when the weak intermolecular forces are broken, these particles will gain what we have kinetic energy. Kinetic energy is simply the energy that is possessed by the particles in motion. The energy that is possessed by the particles in motion is kinetic energy. Therefore, gases will expand more than solids when subjected to the same temperature because gases have what we call a weak intermolecular forces which can easily be broken. Therefore, the molecules within the gas particle will gain kinetic energy and expand. These particles will gain kinetic energy and they will expand. So that is how we explain the particle arrangement in solids, liquids, and gases. We also look at how they expand when subjected to heat. We have gases, they expand more as compared to solids and liquids because of their large intermolecular distance, and they have what we call a weak intermolecular force. Therefore, their particles can easily gain kinetic energy and expand. Another question that we were asked at this point, this question comes from what we call a topic called thermal expansion, and the question reads that state three properties of a thermometric liquid. State three properties of a thermometric liquid. So a thermometric liquid is a liquid that is used in a thermometer. So which properties should we consider when choosing that liquid that is used in a thermometer? That is, those are some of the points that we have to consider when looking at the liquid that should be used in a thermometer. So usually the thermometer is made up of three parts. It has what we call the bulb, it has what we call the constriction, then it has the thin glass tube, and then it has the stem or the glass stem. So usually at this point, maybe I can draw for you at this point. That when using a thermometer, there are some of the factors that we must consider at this point. So usually a thermometer has drawn just a rough diagram to illustrate what a thermometer is. That it has the stem. This stem is usually used for sensitivity. It is made up of a very thin glass, that is to increase the sensitivity, therefore enabling the transfer of heat from your body towards the thermometer. It has this part here looking like a loop. It is called a constriction. A constriction usually enables that liquid to expand. It gives room for expansion of that liquid. That is uniform expansion. We also have what we call a glass stem. A glass stem is usually made up of a transparent material. This is to enable visibility so that you can be able to see the level of the temperature inside. Then this glass stem is usually filled, usually has what we call, it has what we call a calibrated stem or a calibrated scale. The calibrated scale usually has the values of temperature, that is the temperatures of the body of a human being. At this point they lie between 23 degrees Celsius to 37 degrees Celsius. Then whatever we are measuring on right now is the liquid that should be used in this thermometer. What are some of the properties of that liquid? So number one, the liquid that was chosen and that is suitable for use in a thermometer is mercury, because mercury usually has the following property. Number one, the mercury is visible. Mercury is visible. So mercury usually appears shiny, and therefore you can easily see it within a glass tube. Therefore, I will say that mercury is usually visible. Number two, mercury expands and contracts uniformly within a wide range of temperature. It expands and contracts uniformly within a wide range of temperature. This liquid usually it does not have what we call the uniform expansion. It expands uniformly, meaning that when you have 1 degree Celsius, it expands with a certain value. When you go to 2 degrees Celsius, it also expands with a certain value. So it expands and contracts uniformly over a wide range of temperature. That is property number 2 of a liquid that should be used in a thermometer. Property number 3 is that this liquid does not stick within the inner parts of the glass tube. It does not stick within the inner parts of the glass tube. Most of these liquids which stick within the inner parts of the glass tube usually, and the liquids which have a high adhesive force. Also in the same lesson, I'll come and speak about the cohesive and adhesive force. But here, just illustrating, if this is the glass stem, we have liquids that behaves in that manner. When the liquids drop, we have some droplets that will remain in that manner of this liquid. Therefore, the thermometric liquid should not behave like this. It should not stick on the inner parts of the glass tube. These liquids usually stick at this point because they have what we call the high or the strong adhesive forces. That is the force of attraction between molecules of different kinds. So mercury is one of the liquids which does not possess this property. Therefore, the thermometric liquid should not stick on the inner parts of the glass stem. It should not stick on the inner parts of the glass stem. It should expand and contract uniformly over a wide range of temperature, and it should also be visible. So those are the three main properties of a liquid that should be used as a thermometric liquid. So those are the three major points that you should explain when given that question. The next question that we were given is also related to the same, that we are told distinguish between cohesive and adhesive forces. Distinguish between cohesive and adhesive forces. So why do we have cohesive and adhesive forces? I'll give a very simple illustration at this point. That at this point, we have two types of liquids. I have water and I have mercury. So I have water and I have mercury in that manner, so that I have a piece, two pieces of glass, two glasses at that point. In the first glass, I put water. In the second glass, I put mercury. So these are two types of liquid. So when we put water at this point, it appears to take that shape in that manner. When I fill the second glass with mercury, it appears to take that shape in that manner. So looking at the observation, you can be able to see that water tries to raise and it's getting attracted to the walls of the glass. But at this point, on the other hand, that is on mercury, it still raises, but it is not attracted to the walls of the glass. So through this observation is when we came up with what we call the cohesive and adhesive forces. That at this point, we have what we call molecules of the same kind, and we also have what we call molecules of different kinds. So when you talk about molecules of different kinds, we are looking at water. We have the molecules of glass and the molecules of water. These two molecules have been attracted, and therefore, at this point, this diagram gives us what we call the adhesive force. So how do you find this adhesive force? It is the force of attraction between molecules of different kinds. It is the force of attraction between molecules of different kinds. For example, here, it is the force of attraction between the molecules of water and the molecules of glass. At this point, when you look at mercury, now here it gives us what we call the cohesive force. The cohesive force is the force of attraction between molecules of the same kind. It is the force of attraction between molecules of the same kind. This one only happens between the molecules of mercury alone. So the force of attraction between molecules of the same kind will give us what we call the cohesive force. It has been illustrated using that diagram. Also on the surface, you'll find that if you have a flat surface at this point, water when you pour water on a flat surface, it will appear like that. And when you pour mercury on a flat surface, it will form droplets in that manner. This also illustrates the cohesive and adhesive forces. We have the adhesive forces here in water, whereby the molecules of water are attracted to the molecules of the surface. But here we have cohesive force, where we have the force of attraction between molecules of mercury alone. So these are some of the diagrams that might come in your exam, and will require you to actually illustrate the difference between cohesive and adhesive forces. So this question originated from the topic we call force. It talks about forces and define force as a push or a pull. The SI unit of any force is Newton. We also have so many types of forces. We have gravitational force, we have cohesive force, we have adhesive force, we have friction force, we have frictional force, we have centripetal force, we have centrifugal force, we also have the upthrust force. So we have all those kinds of forces which will require you as a student to actually look at them and define them very well. So those are some of the types of forces that we have in physics. So make sure that during your time you go through all the forces in details. The next question that we were given was, state the kinetic theory of matter. State the kinetic theory of matter. And at this point, I'll give a very simple illustration that if I have a piece of paper, and that piece of paper is cut into two, I shall have two pieces from one larger piece. If I again split these two small pieces, I will have four pieces from one large piece. This means that I can be able to cut one large piece of paper into very small particles, so that one large piece of paper can give me up to 100 very small particles. So what does it mean? Is that when you have one molecule, or when you have an atom, is usually made up of very many small molecules. And that is why what matter is. So that when you look at a fault pen like this, we can crush it so that we have a very, very small particles of this pen. Meaning that for us to have matter, then we must join very small particles or very small molecules in order to obtain one atom. Therefore, the kinetic theory of matter usually states that matter is made up of very small particles. Matter is made up of very small particles which are in a continuous random motion. I repeat, the kinetic theory of matter states that matter is made up of very small particles which are in a continuous random motion. The kinetic theory of matter has been well explained using the smoke cell experiment. And if you remember the smoke cell experiment, at this point we're introducing smoke, the smoke cell, inside a closed tube, and then we are going to look at the behavior of the smoke cells. And after some time, you'll identify that these smoke cells usually move in a continuous random motion. They are moving in a continuous random motion simply because there is some form of collision, or in physics we use the word bombardment. There is some form of collision or bombardment between the smoke cell and the invisible air particles. So when the smoke cells are seen to move in a continuous random motion, this means that there is bombardment between the smoke cell and the air particles. And these air particles are moving also in a continuous random motion, only that the air particles at this point are invisible. Therefore, the continuous random motion has been confirmed in all properties of matter, and this has been demonstrated using gases. That the smoke cell experiment is used to prove that matter is made up of very small particles that are moving in a continuous random motion. So you have to take a lot of time and go through the kinetic theory of matter as a topic. Look at the particle arrangement in solid, liquids, and gases. Go through the smoke cell experiment, and each and everything has been explained in details. And I'm also here to clarify the experiments for you. In our next question, the question came and asked, state the factors affecting the rate of diffusion. State the factors affecting the rate of diffusion. And here, first, before we look at the factors affecting the rate of diffusion, I'll first begin by looking at what diffusion is. And at this point, I will say that diffusion is the movement of particles from the region of high concentration to a region of low concentration. Diffusion is the movement of particles from a region of high concentration to a region of low concentration. An example is when you pass along the road and there is a dead dog that is rotting near near the place around that road. You'll be able to discover that there is a smell that will be moving towards you. So that smell is moving towards you as a result of diffusion. Therefore, diffusion normally occurs even when you use a spray. Somebody can be able to identify that you're using a spray. You've used a spray because that smell is moving from where you are, that is a region of high concentration, to other places, which is a region of low concentration. Diffusion normally occurs as a result of temperature and what we call the density. When you increase the temperature, it means that the air particles are going to move very fast. You're going to increase that random motion of the particles, and therefore increasing the temperature will increase the rate of diffusion. Reducing the temperature will reduce the rate of diffusion. So at this point, we usually look at when you increase the temperature and then the particles are moving from a region of high concentration to a region of low concentration, you will identify that these particles are going to move faster when the temperatures are high. And therefore, temperature is one of the factors that affect the rate of diffusion. So if you're told to state among the factors that affect the rate of diffusion, one of them is temperature. That when we have an increase in temperature, at this point we are going to increase the rate of diffusion. When we reduce the temperature, we are going to reduce the rate of diffusion. Another illustration that also affects the rate of diffusion is what we call density. If I break down density into a very detailed and simpler explanation, I can say that density, when you look at density, we simply look at the weight of each single particle of that air. And this one can be demonstrated using two gases. One of the gases that we use is ammonia gas. We have ammonia gas and the HCl gas. So when we have ammonia gas and the HCl gas within a tube, and then the ammonia gas usually is visible, you can be able to see it within a tube. And then we look at the rate of diffusion. You want to compare the rate of diffusion between ammonia gas and the HCl or the acid gas. We want to look at which gas diffuses faster. At this point, we look at ammonia as a gas which has a very low density. The weight of the particles of ammonia are very small as compared to that of the acid gas. And therefore, the density of ammonia is lower than that density of the acid gas or the HCl gas. And at this point, you'll find that ammonia now is seen to occupy the larger space within the glass tube as compared to the acid gas. So this explains that lower density, gases with lower density will diffuse faster than the gases with higher density. A good example is ammonia diffusing faster than the acid gas. So these are some of the factors that affect the rate of diffusion. That the rate of diffusion can simply be affected by what we call temperature and the density. So temperature, increase in temperature increases the rate of diffusion. When you increase the density, you lower the rate of diffusion. When you reduce the density, when the density is low, the rate of diffusion is high. So those are some of the factors that affect the rate of diffusion. Diffusion is also explained using what we call the kinetic theory of matter, because at this point you can also compare diffusion in solids, liquids and gases. And here we explain that diffusion is faster or is fastest in gases as compared to liquids and solids. And when you compare liquids and solids at this point, you'll identify that diffusion is faster in liquids as compared to solids. Therefore, diffusion takes place at a very slow rate in solids. So when you look at the particle arrangement in solids, liquids and gases, you'll find that the gases have large intermolecular distances, and they have what we call weak intermolecular forces. Therefore, they can easily move faster in a continuous random motion, and especially when we increase the temperature. Therefore, diffusion is very fast in solids, and it is faster in liquids than in solids. So that is how we compare the rate of diffusion within the three properties of matter, that is liquids, solids and gases. At that point, under the kinetic theory of matter, when you look at diffusion also, diffusion can occur in solids. Take for example, when you put two solid blocks together, you'll find that for a certain period of time, these two solid blocks will tend to get attached to each other. This proves that diffusion can also take place in solids, not only in liquids and gases. In liquids, you can mix two types of liquids, and you can see two miscible liquids actually combining to form one large liquid through the process of fission. For example, you can mix any colored liquid with water, and the rate of water and that colored liquid will determine how that liquid is going to look like over a certain period of time. Therefore, at this point, we are looking at diffusion within a very large area. That diffusion can take place in solids, liquids and gases. Diffusion can be affected by temperature and density. It is the movement of molecules from a region of high concentration to a region of low concentration. That is simply diffusion. So for a Form 1 student, we have covered the larger part. For a Form 1 student, we have covered the larger part of that revision. So we shall take a little break, and then we shall come back and look at the Form 2 students. So we have a lot that we have prepared for a Form 2 students that we shall be coming up after a short break. So remember to order for exams under the numbers on your screen, and our exams are available on weekly basis. We also we just sell them at an affordable price of 50 shillings. So we are taking a short break, and then we'll come back with the Form 2 revision.
The Fox Adventure. Unstoppable movies. Unstoppable movie series. Unstoppable comedy. Unstoppable adventure. Where entertainment never stops.
What a treat!
Stay home and be safe with the StarTimes aerial decoder and 1-month subscription at 1,499. For inquiries, call us on 0719 077 077. StarTimes. Enjoy digital life. The Fox Adventure. Unstoppable movies. Unstoppable movie series. Unstoppable comedy. Unstoppable adventure. Where entertainment never stops.
What a treat!
Stay home and be safe with the StarTimes aerial decoder and 1-month subscription at 1,499. For inquiries, call us on 0719 077 077. StarTimes. Enjoy digital life. This Easter season, keep the kids safe. More adventure. More education.
Will you please stop it and let my dancing do the talking?
Mommy shark do do
Much, much more fun at home.
Mommy shark do 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 do. Mommy shark. Grandma.
Stay home and be safe with the StarTimes aerial decoder and 1-month subscription at 1,499. For inquiries, call us on 0719 077 077. StarTimes. Enjoy digital life. This Easter season, stay home, be safe. A moment for every man. Marvelous content. Chilling investigative stories. Action-packed programs. The latest news updates around the world.
Trace Mziki is the one and only channel devoted to the very best music straight from the heart of East Africa.
Stay home and be safe with the StarTimes aerial decoder and 1-month subscription at 1,499. For inquiries, call us on 0719 077 077. StarTimes. Enjoy digital life. This Easter season, stay home, be safe. A moment for every man. Marvelous content. Chilling investigative stories. Action-packed programs. The latest news updates around the world.
Trace Mziki is the one and only channel devoted to the very best music straight from the heart of East Africa.
Stay home and be safe with the StarTimes aerial decoder and 1-month subscription at 1,499. For inquiries, call us on 0719 077 077. StarTimes. Enjoy digital life. This Easter season, stay home, be safe. A moment for every woman. Top quality telenovelas.
We have been through a whole lot, but at the end of the day, we
together. Why you think it call us lions?
It's always been Cookie and Lucius.
Variety of dramas,
Because it's absolutely wonderful.
the best local and international shows. Stay home and be safe with the StarTimes aerial decoder and 1-month subscription at 1,499. For inquiries, call us on 0719 077 077. StarTimes. Enjoy digital life. The Fox Adventure. Unstoppable movies. Unstoppable movie series. Unstoppable comedy. Unstoppable adventure. Where entertainment never stops.
What a treat.
Stay home and be safe with the StarTimes aerial decoder and 1-month subscription at 1,499. For inquiries, call us on 0719 077 077. StarTimes.
Coronavirus COVID-19 is a respiratory virus spreading across the world. The infection is spread from droplets of coughing and sneezing of an infected person, touching or shaking hands, or being in contact with contaminated surfaces or objects with the virus. The signs and symptoms are fever, coughing, headache, body ache, difficulty in breathing. The disease can be prevented by regularly washing hands with soap and running water. Avoid close contact with people who have flu-like symptoms. Avoid handshake, hugs, and kissing. Also, protect yourself by covering your mouth or nose using a disposable tissue while coughing or sneezing. If you experience these symptoms and you had traveled or been in contact with a person from a country reporting COVID-19, you should isolate yourself for 14 days. Dial *719# or call 719. This message has been brought to you by the Government of Kenya and its partners.
Hello and welcome to Namanga Girls High School. We are located 5 kilometers from the Kenya-Tanzania Namanga border, in a serene and secure location adequate for learning. We have a science laboratory, a computer laboratory, and a modern library. Our boarding facilities are spacious and clean, with ample water and a backup generator. Our meals are delicious and nutritious. We have vacancies in Form 1, Form 2, and Form 3. Call us today, 0721 925 945 or 0723 144 259.
Ket Girls High School is a girls boarding school located at Kitengela, 2 kilometers along Old Namanga Road. This is a school with good facilities for learning, ample space in class, very good labs for sciences. We teach biology, physics, and chemistry. We have computer labs, very good boarding facilities, and a very good field for sports. We are also good at co-curricular activities, drama, as well as music. For vacancies for Form 1, Form 2, Form 3, call us on 0723 144 259. 0723 144 259. As in Ket Girls High School.
St. Catherine Girls High School, Machakos, a light for society. We are committed to efficient delivery of education, and all our teaching staff are graduates. We impact discipline, commitment, spiritual growth, and high standards of performance in our girls. Our facilities offer the best experience for learners. Our dormitories host 4 students per cubicle. Our classrooms are spacious to facilitate better student-teacher interaction. Our meals are prepared by the school chef, and he never disappoints. We have science laboratories, computer laboratory, and a school health center. Security around the school is adequate, and we have ample space for indoor and outdoor games. We take field trips in our modern school bus and participate in educational activities such as drama, music festival, and science congress. St. Catherine Girls High School Machakos, a light for society. We are located along Masii Machakos Highway at Kaani.
Okay, now we are going to look at some of the questions which were part of our examination, that is for our Form 2 students. I'll be measuring on the key areas that the exam was covering. I'll give the same too much details about the topic, so make sure you take note, have a pen and a paper when going through the TV lessons for it to be very beneficial to you as a learner. Take some points, write down some questions in which you feel they need some clarification, and you can also ask us through our platform, that is Elimu TV. So for our Form 2, I'll start by looking at this question. The question was stating, explain 3 states of equilibrium. Explain 3 states of equilibrium. So this question originates from the topic called the center of gravity. Equilibrium and the center of gravity. On the equilibrium and the center of gravity, we are looking at how the body can be supported within a certain point for it to be either stable, unstable, or neutral. So the point where the weight of the body acts at this point is what we normally illustrate when looking at the center of equilibrium, or what we call the COG. So the 3 states of equilibrium, as I can illustrate at this point, the body can, for example, we have the shape of a cone in that manner. So if it lands or if it rests on the surface in that manner, then we say that this body is in a stable equilibrium. It is in a stable equilibrium simply because at this point it is stable because what we call the COG, or the center of gravity, has been lowered. At this point the center of gravity has been lowered, and also the area of the base has been increased. So when we have a large area of the base and the center of gravity is lowered, then that body settles in that manner, so that we have what we call the stable equilibrium. Under stable equilibrium, when you apply the small force on the body, it still remains to be stable. It remains to be stable because the COG is lowered and the area of the base is wide. Therefore, any force applied does not change the position of the center of gravity. We also have another state of equilibrium, that at this point we have this cone in that manner, so that we have the center of gravity like that, and then we have the flat surface in that manner. So this state of equilibrium, I'll call it unstable equilibrium. It is unstable equilibrium because once you apply a small force on this object, it's going to fall. When it falls, the position of the center of gravity is going to change. So whatever I'm explaining here, you can be able to see that at this point, the area in contact with the surface, that is what we call the area of the base, has been reduced. Number 2, when you look at the position of the COG, it has been raised. So when you try to bend it towards that position or towards this angle, then we are raising the position of the COG and therefore reducing the area of the base. Therefore, when a small force is applied at this point, this particle is going to fall. So this means that it is in a condition known as unstable equilibrium. It is in the condition known as unstable equilibrium because one, the area of the base has been reduced or is very small, and the position of the COG is also raised. So those are the two conditions which makes the body to be in what we call unstable equilibrium. And finally, we have what we call the neutral equilibrium. So how does this neutral equilibrium happens? The neutral equilibrium occurs in a condition such that you have a body lying in that manner along the surface, along the flat surface. So that at this point, you have the position of the COG at that point. So here, at the neutral equilibrium, when I apply a small force on this body, it is going to roll. By applying a very small force, you'll see this body rolling. So it is going to roll. A good example of neutral equilibrium is whatever I'm holding at this point is going to roll in that manner. So that when you apply a very small force, the position of the COG does not change. The COG is going to remain at the same position as this body moves from one point to another. And therefore, we define that condition to be the neutral equilibrium, where the position of the COG does not change irrespective of the force that is applied on the object. So those are the three states of equilibrium. We have stable equilibrium, we have unstable equilibrium, and we also have what we call the neutral equilibrium. So these are the three states of equilibrium that are described using the area of the base and the position of the COG. This is a very important topic that cannot miss in a set of examination, not only for a Form 2 student, but also Form 3 and Form 4. We also normally look at the applications of the center of equilibrium. Some of the applications of the center of equilibrium, of the center of gravity, we can look at what we call the double-decker buses. A question might come and maybe you're asked, why is it important, or why is it risk? Maybe I can frame it like that. Why is it risk for the passengers to feel the upper part of the double-decker bus before feeling the lower part? So this bus is likely to fall. Why? Because when the passengers are going to feel the upper part, when the lower part is still empty, they're going to raise the center of gravity of that bus. So this bus is going to be unstable, and therefore it is going to fall. Some of the questions that have been asked on our KCSE setups are questions like, explain why an overloaded lorry is likely to topple when negotiating a corner. Explain why an overloaded lorry is likely to topple when negotiating a corner. So when a lorry is overloaded, it means the center of gravity of that lorry is going to be raised. We are going to raise the center of gravity, meaning that the area of the base is going to be smaller. So if you're going to have a small area of the base with the COG raised, this lorry is going to be in what we call the unstable condition. So the unstable equilibrium, whenever any small force is applied, or when that lorry is negotiating a corner, it is going to topple because the center of gravity is raised, 1, and 2, the area of the base has been reduced. So the COG is usually applied in many conditions that is in our life, in the society. So a COG can also be calculated, or the center of gravity can also be calculated. For example, when you have a meter rule, you can be asked, where does the weight of the meter rule act? Or if you want to measure the weight of a meter rule, where do you place the spring balance? The spring balance should be placed at the center, that is at the 50 centimeter mark. That is where the center of gravity of that ruler will be acting. So under the center of gravity, we also look at what we call the moment of a force. The moment of a force can simply be defined as the product of force and mass of a body. It is the product of force the force and distance of a body from the point of equilibrium. The product of force and distance of the body from the point of equilibrium. That is what we call the moment of a force. It is calculated what we call Fd. F is the distance, is the force, and D is the distance. The SI unit for measuring moment of a force is simply Newton meters. So we also have what we call the law of moments, and the law of moments usually states that the sum of clockwise moments at a point is equivalent to the sum of anticlockwise moments from the same point. The sum of clockwise moment at a point is equivalent to the sum of anticlockwise moment from the same point of support. So those are some of the key points which we normally look when we are looking at the states of equilibrium and the center of gravity. This is one of the topics that has most applications. It has so many applications when it comes to exams. So you have to read in order to have all the content in full details. Another question that was asked, and I brought it closer because it's related to our first question, is that state two ways in which you can lower the stability of an object. State two ways in which you can lower the stability of an object. So one of the ways in which you can lower the stability of an object, to lower the stability is to make it topple, to make it fall. So in order to make an object to fall, number one, or to lower the stability of a body, number one, make sure that you raise the center of gravity, or you raise the C or G. So by raising the C or G of a body, you are lowering its stability. Number two, you reduce the area of the base. When you reduce the area of the base, you're also making that body to be stable, to be unstable. So those are the two ways in which you can lower the stability of an object. Lowering the stability of an object. The opposite of this question is increasing the stability of an object. So you need to know the difference between lowering the stability of an object and increasing the stability of an object. Those are the two key points in which, as a student, you have to distinguish. Another question for a Form 2 students comes from what we call the magnetic shielding. What is magnetic shielding? This is a point which I've illustrated in our previous lesson, that is in magnetism, and I hope as a student who has been following Elimu TV, this is one of the easiest questions. That magnetic shielding, we refer to properties which have the ability to concentrate magnetic fields and therefore preventing them from reaching certain region. These are materials with properties that are able to concentrate magnetic fields and therefore preventing them from reaching certain region. Some of this material, or an example of this material, is iron. It usually prevents the magnetic fields from reaching certain regions. And by drawing, I can be able to illustrate here that at this point, if you have a north pole and you also have a south pole of a magnet, and then at this point I have what we call the iron ring. Therefore, we are going to have these magnetic fields originating from the north pole. They go in that manner towards the south pole in that manner. So this is how the concentration is going to occur. The magnetic fields are going to be concentrated in that manner. Therefore, at this point, we are going to have another point here, which is called a neutral point. At this point, you're not going to have any magnetic field. The magnetic fields have been concentrated from reaching this region, simply because we are using what we call a soft magnetic material. An example of a soft magnetic material is what we call the iron ring. It is used to concentrate the magnetic material. So that is what we explain under magnetic shielding. This application is used in watches. It is majorly used in stopwatches. It is also used in speakers and other devices that use permanent or that is permanent magnets. Then another question was to distinguish between electromagnetic waves and mechanical waves. Distinguish between electromagnetic waves and mechanical waves. So at this point you're looking at two types of wave in terms of transmission. So the electromagnetic waves, these are waves that do not require material medium for transmission. They are waves which do not require material medium for transmission. That is electromagnetic waves. An example of an electromagnetic wave is light. Light does not require material medium for transmission. You can be able to use light anywhere without a medium for transmission. For example, you can use light inside a vacuum. You can also use light in space. You can use light in air. Light can operate anywhere. Therefore, light is an example of an electromagnetic wave. And electromagnetic waves have illustrated that these are waves which do not require any material medium for transmission. The opposite of electromagnetic wave is what we call the mechanical waves. Mechanical waves are types of waves which require material medium for transmission. An example of a mechanical wave is sound. You cannot use sound without the means of transmitting this sound. Sounds require material medium for transmission. For example, microphones are connected to wires. These wires that are connected to microphones usually provide material medium for transmission. You cannot be able to speak in a vacuum. Sound cannot be transmitted in a vacuum. Therefore, there is no medium at that point. So for us to have sound, therefore sound usually require material medium for transmission. We also have another topic in Form 2 that speaks about sound, and it talks about sound can be transmitted using what we call velocity. And the velocity of sound can be affected by three things. Number one, the temperature of the air. When the temperature of the air is high, the air molecules are going to expand, and therefore they are going to move faster because you're going to break their weak intermolecular forces. Therefore, sound is going to be transmitted faster. Number two, humidity of the air. Humidity is the amount of water vapor in the atmosphere. So when the humidity is high, then the velocity of sound is going to reduce because the amount of water vapor in the atmosphere is going to contract the water molecules. Therefore, it does not have the ability to break the weak intermolecular forces. Number three, we shall also look at the direction of the wind. Direction of the wind usually increases the velocity of sound. If you speak along the direction of wind, therefore the sound is going to be transmitted very fast. So sound is a good example of mechanical waves that is still explained under the waves that require material medium for transmission. When you look at waves, waves is very large. It is simply, a wave can simply be defined as a disturbance that is transmitted through a medium. Waves have what we call wavelength, they have what we call frequency, and we also calculate the velocity of the wave. So the wavelength of the wave is simply the distance between one crest and another, or the distance between a trough and another. So when you have a distance between one trough to another trough, we have a wave. Then we have what we call the amplitude. Amplitude is simply the maximum displacement on either side of a wave. The maximum displacement on either side of a wave. That is what we call the amplitude. Then we have the frequency. The frequency is the number of oscillations that can be made by a wave in 1 second. The number of oscillations which can be made by a wave in 1 second is what we call the frequency. Putting my illustration on the wave, I shall come and draw a very small diagram at this point, so that at this point I want just to give you an illustration or an idea of waves, because we have some students who will need more illustration on the same. That at this point, if I have my figure at this point in that manner, that is a graph. So at this point, what we have here is the amplitude. So the amplitude is the maximum displacement of a wave on either side. So that this amplitude, it is either positive or negative in that manner. So that at this point, the wave travels in that manner. So that the distance between a trough and another trough in that manner is what we call the wavelength. So this wavelength is usually measured in meters. It is the distance between a trough and another, but it can also be described as the distance between one crest and another. Then, under the same wave, we have another term called frequency. Frequency is normally denoted using letter F. The SI unit of frequency is Hz or Hertz. So this frequency, we usually define it as the number of oscillations that can be made by a wave in 1 second. The number of oscillations that can be made by a wave in 1 second. That is what we call frequency. So we have frequency, we have wavelength, and therefore we also have the velocity of a wave. So the velocity of a wave is usually calculated by just take the wavelength of a wave. This point that you have V is equals to F times the wavelength in that manner. So that is how we calculate the velocity of a wave. Check F, which is the frequency, and the wavelength is we normally use this sign for wavelength. This sign is known as lambda. Lambda is a sign used to calculate wavelength. So for you to calculate the velocity of a wave, then take F multiplied by lambda, where F is the frequency and lambda is the wavelength. So that is how you can be able to calculate the velocity of a wave. Waves usually have amplitudes, and amplitudes can be read directly from the graph. You can be able to read the amplitudes of this wave directly from the graph. The amplitude can either be positive or negative. This is because we have defined it as the maximum displacement of a wave on either side. So we shall be able to look at some much in our next lesson, some much calculations on waves, how you can be able to calculate using those formulas. Another question that was asked or that was posted was state Hooke's law. And then in addition to that, write the equation that proves Hooke's law. So what is Hooke's law? Hooke's law came as a result of helical material. A helical material is simply a stretching material, like a rubber band or a spring. So when you pull any stretching material, for example this one, when I pull it, you'll find out that an increase in force, when I increase the force, I am going to increase the extension. When I pull it more, the extension increases. But if I continue pulling it, I reach a point where this material does not pull anymore. And therefore, it can either break or it will acquire what we call the permanent change in size and shape. That is what we call deformation. Deformation is simply the permanent change in size and shape of a helical material. Therefore, this person called Hooke's gave us what we call the Hooke's law, which says that the extension of a helical material is directly proportional to the force, provided the elastic limit is not exceeded. I repeat that the extension of a helical material is directly proportional to the force, provided the elastic limit is not exceeded. So at this point, using the proportionality sign, I'll be able to prove for you the Hooke's law at this point. So that we're having the force at this point being directly proportional to the extension. Extension of a helical material is the length in which it acquires after being pulled. So that we are told the force is directly proportional to extension. So that this means that when you increase the force, the extension of that material also increases. To remove this proportionality sign, we introduced a constant K, so that F is equals to K E. This is the equation that proves Hooke's law. The K at this point is what we call the spring constant. The K at this point is what we call the spring constant. This is the spring constant of a spring. It is called the spring constant because the constant does not change. The extension can increase, we can increase the force, but the constant will always remain to be the same. This is the value of K, which we call the spring constant. So this is the equation that proves what we call the Hooke's law of a spring. And the Hooke's law itself, we have said, it says that the extension of a spring is directly proportional to the stretching force provided the elastic limit is not exceeded. So there is also much about Hooke's law that we shall be able to look at. We shall be able to look at how to calculate the energy of a spring. We shall also be looking at how the graph varies of force and extension. We have so many questions that are there to come for us. But as we also continue, apart from Hooke's law, there's a question that we had that was posted, and the question was stating that set the reading on the micrometer screw gauge. Set the reading on the micrometer screw gauge. So this question originates from measurement 2, and I will combine the two questions, that is on the micrometer screw gauge and the vernier calipers, and we shall be able to look at all of them. So that at this point we have the micrometer screw gauge and the vernier calipers. These are the instruments that are used in measurement. So the micrometer screw gauge is used to determine the diameter of very small objects. For example, the diameter of a wire. The diameter of a wire can be determined using the micrometer screw gauge. So the micrometer screw gauge usually has two scales in that manner. So that if I can be able to draw it, it appears like that. That is the micrometer screw gauge. It usually has the scale. For example, you can have 30, 31, 32 in that manner. Then at this point, you can have this one as 50, 55, 60. So that usually in the micrometer screw gauge, we have two types of scale. We have the main scale and the thimble scale at this point. So you, what we are required to do for you to take measurement on a micrometer screw gauge, simply take the values on the main scale, which is 32 here, plus add the value on the thimble scale. The value on the thimble scale is usually multiplied by what we call the least count. The least count at this point is 0.01 multiplied by 55, which can be directly read from the scale. So that here we shall have our value as 32.55. Remember, because the micrometer screw gauge is usually used to measure the diameter of very small objects, therefore it has its scale or its units calibrated in millimeters. So that this value at this point becomes mm. It is in millimeters because it can be used to measure the diameter of very small objects. This question has been posted most of the times, that it's explain why the micrometer screw gauge, or which instrument is the best for measuring the diameter of very small objects. Which instruments is preferred for measuring the diameter of very small objects? At this point, we prefer the micrometer screw gauge. It is the micrometer screw gauge because it has what we call the thimble scale and the main scale, which can be used to measure the small diameters, for example, the diameter of a wire. We also look at, on the same case, what we call the vernier calipers. The vernier calipers usually also has two scales at this point, so that It looks like that. So it has two scales. It has the main scale and what we call the sleeve scale in that manner. So usually on the vernier calipers, on the two scales, we usually look at where the two values coincide, or where this, the main scale, the value of the main scale matches with the value on the sleeve scale. So for example, at this point, we have 0. So you count 0, 1, 2, 3, 4, 5. So it is 0, 1, 2. So this value is 2. Plus, we are going to look at where the two values coincide, where the value on the main scale matches with the value on the sleeve scale. Where do they match? They match here at 5, 6, 7, 8. They match at 8. So at this point we are taking 8 multiplied by the least count. Our least count is simply 0.01. So we have 2 added 2, we have the bracket, we have 8 and 0.01. The least count is simply the measurement between one value on the scale and another. Between two calibrated values on the scale, we have that distance. That distance is what we call the least count. And the least count in our case here on the vernier calipers is simply 0.01. So taking this value, you have 2 plus 0.08, you have 2.08. Something that I also have to remind you about the vernier calipers. It has the outer jaw and the inner jaw. So it can be used to measure the diameter of at least some large objects. For example, the top of a bottle, you can be able to get its diameter using what we call the vernier calipers. Therefore, it has two jaws, and therefore, because it's larger, it's used to measure diameters which are larger as compared to the micrometer screw gauge. Its units are written in centimeters. So that is one of the differences between the micrometer screw gauge and the vernier calipers. The micrometer screw gauge has its units in millimeters. The vernier calipers has its units in centimeters. Then the micrometer screw gauge is used to measure the diameter of very small object. The vernier calipers is used to measure the diameter of at least large objects. So all of them have also what we call the zero error. The zero error can be determined by looking at when you rotate, for example, the micrometer screw gauge until it clicks, the two values of 0 on the two different scales should match. If they don't match, then you have a zero error. The zero error can either be positive or negative zero error. When the zero error is positive, then that value of that of the error should be subtracted from the final answer. I repeat, when the zero error is positive, then that value of the error should be subtracted from the final answer. And when the zero error is negative, then that value of the error should be added on the final answer. So before you use either a micrometer screw gauge or a vernier calipers in your practical, ensure that you are able to confirm whether it has a zero error. Then you should distinguish whether the error is either positive or negative. So that is how we handle questions when it comes to micrometer screw gauge and the vernier calipers when it comes to our exams setup. So those are some of the very easy questions that come from measurement 2. That is the topic measurement 2 under that is a form 2 topic known as measurement 2. It looks at the vernier calipers and the micrometer screw gauge. Finally, I will finish by explaining what we call the oil drop experiment. there is one question that came from the oil drop experiment, and the question reads, if an oil drop of diameter 0.5 millimeters spreads to form a patch of diameter 0.2 meters, estimate the thickness of the molecule. If an oil drop of diameter 0.5 millimeters spreads to form a patch of diameter 0.2 meters, estimate the thickness of the oil molecule. So I'll give out an experiment here. I'll draw an illustration as we go so that it is understood very well that at this point we have what we call an oil patch and an oil drop. So you want to look at the distinction between a patch and a drop before we go to our calculation. So that at this point I have a container. This container is filled with water in that manner. So that at this point I have water. So that when I have water in that manner, I'm going to drop, or I'm going to splash some form of dust on top of this water. This means that the dust is going to float on water, so that I'm having some dust here. This dust is going to float on water. So when this dust is going to float on water, I'm going to drop an oil. So this is an oil drop. It's moving in that direction to fall on this dust which is flowing on water. This drop will fall on this dust to form what we call a patch. Now, this is what we call a patch. A patch usually appears in form of a cylinder. A drop usually appears in form of a sphere. That is where most of the students get confused about this oil drop experiment. That when you talk about a drop, we are talking about an oil in spherical shape. When it lands on the surface of dust, it forms a patch. A patch, we are talking about an oil in cylindrical shape. And therefore, using the two, we can be able to estimate the height or the size of this patch. How do you estimate the size? If I have the drop in spherical shape in that manner, take the volume of the sphere. The volume of the sphere is simply 4/3 take pi r cubed. The volume of a sphere, it is 4/3 pi r cubed. You don't have to remember that formula because you can find it in your mathematical table. The volume of a patch, which is a cylinder here, at this point, is pi r squared multiplied by h. Pi r squared is the base area, we are multiplying by h. So the h at this point is the size of the patch that we want to estimate, meaning that this oil drop is falling on the dust to form what we call a patch. So when you change the shape, the volume remains to be the same. So that is one of the ideas that was being expressed under the oil drop experiment, that when you are changing the shape, as much as you might change that shape, the volume will always remain to be the same. Or assume, for example, you take a piece of clay to mold a car. That car that you molded using that piece of clay, you can also change it to mold a cart. So the volume of that cart that you molded will be equal to the volume of that car. Meaning that once you change the shape, it does not affect the volume. The volume remains to be the same. So that at this point, this patch has fallen on the dust. This drop has fallen on the dust to form the patch. The drop was in a spherical shape, and now the patch is in a cylindrical shape. Therefore, the shape of this oil molecule has changed, but the volume remains to be the same. So that here you can be able to equate that the volume of the drop is equal to the volume of the patch. The volume of the drop is equal to the volume of the patch. Therefore, if the volume of the drop is equivalent to the volume of the patch, you can say that the volume of the sphere, which is 4/3 pi r cubed, is equal to the volume of the cylinder, which is pi r squared h. So I want to finish by giving you the formula now for calculating the size of the oil molecule before you handle that question, so that at this point if we are taking the volume of the drop to be equivalent to the volume of the patch, then 4/3 pi r cubed is equivalent to pi r squared h. At this point, I'm using small r and capital R because the radius of the drop is different from the radius of the patch. Although the two volumes are equal, the radius of the drop is different from the radius of the patch. And that is why one radius we use capital R, another radius we use small r. And you can be able to identify from our questions that we have two different radius in our questions that we must use to estimate the size of the oil molecule. Therefore, I want to remain with h, which is the size. Therefore, I divide here by pi r